We're going to start off with a little bit of review. Our recording is going now, so please keep the noise off. Let me get to the right spot here. A couple of quick things that I'll review first. We talked about that acronym CHNOPS, the carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur thing, and how those are the 6 most important elements to life. We spent quite a bit of time talking about nitrogen. Where do we say most nitrogen is at on Earth?
In the air.
In the air. And what's the problem with that?
You can't use it.
Can't use it because what holds the two ends together? Triple covalent bond. Really hard to break, and the only kinds of things that can break it are what kinds of things? Bacteria mostly that are found in the ground, in the oceans, sometimes found where in the area? On certain plant roots. One thing that we're going to talk over and over again in this class about are what are called biogeochemical cycles. Well, that's not going to work. I don't know exactly what it's doing there. It might work eventually. Look at that. There we go. It's caught up. Biogeochemical cycles. Take that word and think about it for a minute. Bio means life. Geo means earth. Chemical. So it's basically this. How do chemicals on Earth move through living things? What's an example of a biogeochemical cycle? There's 4 of them that you ought to know something about. One we just talked about. Nitrogen cycle, carbon cycle, oxygen. Sometimes we talk about the oxygen cycle, not usually though. Water cycle, and one more. Phosphorus. Those are the 4 biogeochemical cycles I want you to know something about. Phosphorus, water, carbon, and nitrogen. Let's go back and talk nitrogen for a second. We talked about how that most nitrogen is in the air, and what's the molecule that nitrogen is in the air as? N2, right? What's the process called where the bacteria take that N2? It's called nitrogen fixation. They convert the nitrogen gas into what 2 ions? Nitrate, NO3 minus, or ammonium, NH4 plus. Now, if that's the only thing that happened, what would eventually happen to all the nitrogen in the air? If bacteria were constantly turning nitrogen gas into ammonium and nitrate, it'd all go away eventually, right? That's not happening. So what must also be happening? There are different bacteria in the ground that do the exact opposite. They take those nitrates and ammoniums and turn them back into nitrogens. That happens in the ocean, it happens into the ground. That process is called denitrification. So denitrification is the opposite of what? Nitrogen fixation. Those 2 things make up what we call the nitrogen cycle. Nitrogen fixation takes N2 out of the air, breaks that triple bond, and converts it into ammonium or nitrate ions, things that animals and plants can use. Other bacteria in the ground convert these 2 back into N2 gas. That's called denitrification. And it's a cycle. How have we as humans screwed up the cycle in some ways? What do we figure out how to do sometimes between World War I and World War II that screwed up the nitrogen cycle? We figured out how to make fertilizers, artificial fertilizers. If you look on the label of most artificial fertilizers, what's in them? What chemical? If you went to Home Depot and you bought a bag of fertilizer, what's the label going to say on the product? This is ammonium nitrate. That's what it is. It's both of those things. Ammonium nitrate. Why has that screwed up the nitrogen cycle? Why is making fertilizers kind of a problem sometimes? Let's say you're farming down in one of those fields near Mount Carmel, and you grow in maybe cotton. You have fertilized cotton, so you fertilize your cotton, make it grow. Where does a lot of that fertilizer end up eventually? In the river. It's not supposed to be there. What kinds of things live in the river other than your obvious fish and crawdads and stuff like that? Yeah, microorganisms, algae, bacteria. Normally there can't be too many of those there because there's not very much what in the water? Nitrogen. Nitrogen is what we call a limiting factor. But all of a sudden that nitrogen gets in the water that's not supposed to be there. And what happens to the algae and the bacteria? They go crazy. They reproduce like bonkers. What do we call that if it's algae? When they just grow out of control and everything turns green because of it. It's called an algal what? You guys ever heard of an algal bloom? Algae bloom, sometimes it's called. They grow out of control. And that can be a problem. It can be a big problem. A lot of times we screwed it up in another way. Let's say there's no farmers around Mount Carmel. But you go down to the river and the river's all thick and green and soupy looking. What else might be causing that other than farms? What other human kinds of things puts a lot of nitrogen into the ground and therefore into the water? No, not pesticides. Septic tanks. Okay? Sewage. Your poop has a lot of nitrogen in it. Okay? And eventually, if the septic tanks are close like Mount Carmel is to the river, a lot of that sewage eventually seeps into the river. And that causes the algae to bloom. If you canoe down the river near Mount Carmel, the water's kind of green in certain spots. That's part of the reason. Okay? Another place where it's really green is near where? Anybody canoe by the Flint River? I do a lot. Where's the greenest spot on the Flint River over there in that general neighborhood? By the dump. You guys ever know where the dump is there by Mount Carmel School? Okay. If the river goes right behind that, if you canoe that part of the river, there's always all kinds of green stuff in the water. Because what's there a lot of in the water? Maybe, or it may not be fecal matter, but it's some kind of nitrogen-containing stuff coming from that dump. So we've messed with the nitrogen cycle. Let's talk about phosphorus for a minute. And the phosphorus cycle. Where did we say most of the phosphorus on Earth is at? We might not have talked about that again, I'm not sure. It's in rock. Phosphorus is usually found in rock. How does it get out? Erosion, weathering, rain, wind, that kind of thing. It gets out, it probably first gets taken in by what? Yeah, plants, maybe bacteria. Becomes part of their bodies. We eat the plants, we eat something, we get our phosphorus that way from eating other things. Eventually, though, that phosphorus probably ends up in something dead, right? And that dead thing gets buried and eventually turns back into what? Well, sometimes back in the dirt, but let's say whatever it's in falls down into the ocean and sinks way down in the bottom. What might eventually get turned into if the right pressure and stuff is right? Rock. So it's trapped down there in the rock again, and maybe it's 100,000 feet down, and one day the sea levels rise and that rock's back on top again, and now it erodes and weathers and it's back in circulation again. So it's from rock to usable phosphorus, back to rock, back to usable phosphorus, back to rock, and so on, back and forth. That's the phosphorus. The other one that we'll just briefly mention today, we'll spend a lot of time on it in the next couple of weeks. It's the carbon cycle. Where's most carbon on Earth now? In organic matter, in living things. Every time though a living thing, let's say you're a dinosaur, and you ate Kool-Aid right here. You're a T-Rex, you just ate Kool-Aid. To get energy out of it, what do you have to do to pieces of Kool-Aid? What process allows you to get energy out of Kool-Aid? Well, after digestion. What's the process that lets us chemically get energy out of food? Maybe the most important process on Earth. cellular respiration, right? You guys know about cellular respiration? That lets us take food and use the energy out of the food to make what? What's our energy source in our body? What chemical? ATP. Cell respiration lets us make ATP. But as we're digesting Kool-Aid and doing cell respiration on him, the pieces that we can't use, what do we do with pieces of Kool-Aid that we can't use? Get rid of it as what? Mostly. What kind of waste? What's Kool-Aid mostly made out of? Carbon. Okay? So how do we let go of that carbon that we can't use? We breathe it out. That's what? CO2. The CO2 that you're breathing out right now is from food you might have ate last night. Every time you eat, the gas you're breathing out is like the waste products of what you ate. Well, that's cell respiration. Taking food, getting energy out, and the carbon that you can't use is breathing back out into the air. Well, what has the ability to take that carbon in and reuse it? Plants, right? Plants and algae and some bacteria take in that carbon and use it to do what? What process? Photosynthesis. And then that photosynthesis is used to make living things again, right? So the carbon's taken out of the air, used to build living things. And it just keeps cycling like that. Cell respiration gives off the carbon, photosynthesis uses it. Cell respiration gives off the carbon, photosynthesis uses it. It's just a cycle. How have we screwed up that cycle? The carbon cycle. How have we messed with it? What did you do to get here to school today? Car. And how did your car work? You burned gas. Okay? Gas is mostly made out of what? Carbon. When you burn it, what does that release? Lots of CO2. So because of human activities like burning, what's constantly happening to the amount of CO2 in our atmosphere? It's going up. And a lot of people think that that extra CO2 in the air is causing what to happen? Has nothing to do with ozone hole. What do they think more CO2 is causing? Global warming, which is a completely separate problem than what you're describing. Now, after this summer, that might be hard to believe, right? This is the coldest summer in my lifetime in Alabama. But a lot of people think that all this extra CO2 sort of acts like a blanket, like a transparent blanket, a see-through blanket. Because what can come through the blanket with no problems? The sunlight. So the sun comes, what should happen in a day normally to the amount of sun energy in and heat energy out? It should be equal. But what people who believe in this idea of global warming believe is that the CO2 acts like this transparent blanket. Light comes in, no problems, but the blanket slows down what? The heat going out. And if more light energy comes in and heat energy goes out, what's the only thing that could happen? If you got more coming in than going out, what's going to happen? You got to heat up, right? That's a political, scientific quandary. Nobody really knows the answer to the global warming question. You'll hear some people say there's no doubt man burning gas is causing the Earth to get hotter. They're lying if they say that, because nobody's sure. There are other people that think what's causing it. Well, maybe, but a lot of people think it's the sun. The sun isn't always giving off as much heat. I mean, there's been, way before humans, there were ice ages and then there were hot times, right? Some people think that it's caused by solar activities, solar patterns. We don't really know. But there's no doubt that we've messed up the carbon cycle by burning things, putting more carbon into the air. What else have we done that's caused there to be more carbon, other than just burning? Yeah, cutting down trees, because what are trees doing? They're taking it out of the air. And every time we cut one down, that's more carbon dioxide that stays in the air. Not only trees, but just, putting parking lots where there used to be grass. That's a big deal too, right? It's cutting down the plants that are taking in that carbon. So those again are called biogeochemical cycles. You will hear me talk about those over and over and over again. Make sure you're familiar with them. Josh, got a question? Say again? Yeah, we're going to save the water for later. We won't talk about the water cycle so much. Mostly we're going to talk about carbon, phosphorus, and nitrogen. Let's get back to some chemistry here for a minute. If you have two non-metal atoms, and they're going to bind to each other, how do they bind? What kind of bond do they form? Non-metal to non-metal. Covalent. And we know in covalent bonds, what happens? The sharing of valence electrons so that they both can eventually get up to what? 8. And what do we call the 8th thing? What's this? It's an octet, right? Having 8. What does it mean when an atom gets 8 valence electrons? It's stable. It's not reactive anymore. Now, on the other hand, if you have a metal binding to a non-metal, what kind of bond is going to form there? That's ionic. And let's just look at an example. Let's say we had calcium, and we were going to bond that to fluorine. That makes it really hard to write. Okay. How many dots should we draw around our calcium? 2, right? It's in column 2. It's got 2 valence electrons. This is really going to be fun. I don't understand, but okay. And then the fluorine, how many dots there? 7, right? I'm not even going to attempt to draw those. But we know to be stable, what's the fluorine got to do? It's got to get 1, right? So it'll take 1 from calcium, no problems. And when it does, the fluorine becomes what? Stable and what charge? F minus 1, right? It becomes an anion. What's got to be in this picture to make it work? What else needs to be there other than what we've got drawn up there? Another fluorine, right? Because the calcium has to get rid of how many? 2. Fluorine can only take 1. So that's why the formula for calcium fluoride is what? CaF2. Because there's got to be 2 fluorines to take those 2 electrons. What's going to happen to the calcium once it gives both of those away? It's going to be plus 2. And what's actually going to hold them all together? The Ca and the 2 Fs. What makes an ionic bond work? Plus attracts minus, right? It's an electromagnetic kind of deal. Which one do we say stronger? Ionic or covalent? Covalent. Much stronger most of the time. Let's go a little bit further. We spent quite a bit of time talking about polar. Let's make sure we know what polar means. Polar means a molecule has what? A positive end and a negative end. It's not ionic. It's caused by atoms that are what? What causes a molecule to be polar? It has to have an atom in it that's very what? Electronegative. And we said before, the only 2 elements in biology you really need to worry about that with are which 2? What are the 2 electronegative things that are going to cause issues in biology? Oxygen and nitrogen. Fluorine and chlorine, they're really electronegative too, but they're not all that important usually in biology. So it's going to be either the nitrogen or the oxygen that cause that issue. When you hear the word polar, what's the first molecule you ought to think about in biology? What? In water, the hydrogen end of the molecule is always what charge? Positive. And oxygen's negative, because it's really electronegative. And what does that mean happens when you get 2 waters near each other? They stick. And what's that bond between 2 waters called? A hydrogen bond. And it's an example of what kind of bond, since it's between molecules. Intermolecular, right? What's a bond like the bond between an H and an O in the water molecule called? Inside the water molecule. That's intra. Which one's stronger? Inter or intra? Intra is way stronger. Hydrogen bond's kind of weak. But in an ocean of water, how many hydrogen bonds are there? A gazillions. That's not even a real number, I don't think. But there's a bunch of them. And collectively, they can be strong, even though individually, they're kind of weak. We said water stick to water by these hydrogen bonds. What's the word for when something sticks to something like itself? Cohesion or cohesive? Water also sticks to what other kinds of things? Anything that's polar. And what's that called when water sticks to a paper towel? Adhesion or adhesive. So when something sticks to itself, that's cohesion, water to water. And when things stick to other polar things, that's called adhesion. Polar always likes to mix with polar, right? Will water mix with alcohol? Like ethanol. The water and ethanol mix. Yeah. When people drink beer, they're drinking mostly what? Mostly water. With a little bit of alcohol in it, right? Does the alcohol floating on the top of the can? No, it's all mixed in there equally. They mix. What does that mean about ethanol? It's polar. Right? They mix together. They mix pretty evenly. So polar things will mix with polar things, and non-polar things will what? They mix with non-polar things. Like dissolves like. That's sort of this saying that we use. Like dissolves like. Polar will dissolve in polar. Non-polar will dissolve in non-polar. All right, we're going to do these clicker things. We might have already done these first couple, but we're going to do them again just for the sake of review. So get your little clicker, make sure it's on. And go ahead, once the numbers come up, and click in your answer to that question. All right, go ahead and get in and answer. Anybody have 8 or 9? Clicker 8 or 9? All right, 9. What about 14? Okay, you can change it, but do it quickly. All right, we're going to call it there. Answer is, I hope obvious to you, is C. And remember that water is polar because it's got what in it? What element makes it be polar? Oxygen. Oxygen is very, very what? Oxygen is very electronegative. All right, let's move on to the next one. Again, you've got another little clicker question here. Go ahead and key in your answer to that one. All right, is that everybody? Hoping the answer to this one was obvious to you too. Should have been B. Most of you got that. Let's take a minute and look a little more closely at these choices though. The bind between C and H in methane. What kind of bind would that be if it's in methane? That would be an intramolecular force, right? What kind of bind would it be if it's between carbon and hydrogen? Speak up. Between carbon and hydrogen, what kind of bind would it be? It's 2 nonmetals. What kind of bind would it be? Covalent, right? It'd be a covalent bond. We know B is the answer. Let's go down to C. What kind of bond would that be if it's between sodium and chloride? It has to be ionic, right? Because you got a metal to a non-metal. That's an ionic bond. And then D, two hydrogens, the bond between two hydrogens. Hydrogens are both non-metals, I think, right? So what kind of bonds it got to be? Covalent. A little bit of review of ionic bonding before we get into any new stuff. We know ionic bonds form between metals and nonmetals. In an ionic bond, the metals tend to lose electrons and become what kind of ions? Positive. Cations, what we call those, right? And the nonmetals tend to gain electrons, become negative. What's the word for that? Anions. And what holds the two things together is that positive attracts negative force, electromagnetic force. Another thing to remember about ionic bonds, compounds that are ionic we call salts. Anything that's held together with ionic bonds, that's a salt. And salts dissolve really, really well in water. Any kind of ionic thing dissolves well in a polar solid. That's an important thing to know. And what we're going to look at for most of the rest of the time today is this stuff. The unique properties of water. Like we said in here before, anytime scientists are looking on different planets or asteroids or wherever for life, the very first thing they always look for is what? Water. And the assumption is no water means no life. That might not be a good assumption. We may be completely wrong. But that's the assumption right now. And the reason it's the assumption is water has all kinds of properties that are really important for life. And most of those properties that water has are due to the fact that, number one, water's polar, and number two, it can make hydrogen bonds. Those two things make water really, really unique. It's polar, really polar, and it can form hydrogen bonds with other molecules. So let's start off and talk about one of water's most basic properties, and I think we talked about this one a little bit the last time. Sometimes water is called the universal solvent. What does that mean? If you're the universal solvent, what does that mean? What's a solvent? Something that can dissolve other things. If you're the universal solvent, what does that mean? You can dissolve about anything. Water can dissolve just about anything given enough time. Up until about maybe 15 years ago, what did they use in the United States to make pipe out of? Like water pipe, like the pipes. Well, no, they used to use lead way back, but not 15 years ago. Use copper. Let's say you started off when you built your house, and your copper pipes were, I don't know, maybe yay thick. After like 30 years, if you cut open one of those pipes, what would it look like on the inside? Might be like, probably not like that. But you get the point. It gets thinner and thinner because the copper's dissolving. And what's going to start to happen to those pipes? They're going to start to leak. The water's dissolving the copper. You've been drinking copper all those years. It's not a bad thing. You need some copper. But it's bad when you start having to fix all those leaks. But water being the universal solvent is hugely, hugely important because 70-something% of your body is what? Water. 70-something% of your blood is water. And if things won't dissolve in water, you can't what? You can't move them around. You can't transport them. So the fact that water will dissolve just about anything is huge because it allows us to transport things inside our body. It allows the phosphorus cycle to happen, right? Because what's got to happen for phosphorus to get into us? Where do we say most of phosphorus is at? In rock. So what did water better be able to do? Dissolve the rock, right? The importance of transporting things is huge for water being the universal solvent. Now I'm going to assume you guys already know what these other terms mean, but Let me briefly mention. What's a solute? The solute's the thing that gets dissolved. So if we're talking about making salt water, water is the solvent, salt is the solute. And when we mix them together, now we have what? A solution. And solution is what you get when you mix the two together. I'm going to skip capillary action for just a second and surface tension. And I'm going to go down and talk about water having what's called a high specific heat. Think of a water molecule like a single X. And I would draw it up here on the board, but that's not cooperating very well. When water's in its liquid form, the waters are all hooked together in chains. Like so. And the bonds between each one of those X's, what do those bonds represent between the water molecules? What kind of bonds hook one water molecule to another? Say again? Hydrogen bonds. Well, let's say that you've got that water in a cup. Let's say in a glass. And you start applying heat to that glass. Put a thermometer in there. At first, the temperature of the water doesn't change very much. Because what's temperature actually measuring? What does temperature measure? The movement of molecules. When you first start heating that cup of water, the heat's not being used to move the molecules faster. What's the heat being used to do? Break the molecules apart. Break these hydrogen bonds, right? It takes a while to do that because there's a bunch of them. Once most of them get broken, then what is the heat used to do? Speed up the molecules. That's when the temperature starts going up, right? But because water is held together with all these hydrogen bonds, its temperature doesn't change very much when you heat it up. And that turns out to be really important. Because what are you mostly made out of? Water. You go out on a day like yesterday was pretty warm, but let's say we had a 105 degree day. You go out on a 105 degree day, if you were made out of, let's say you were made out of rubbing alcohol instead of water. You're 70% rubbing alcohol. You walk out. What happens? Your temperature spikes up, you may start to boil really fast. Because water has a low specific heat. It's easy to heat it up. Alcohol has a low specific heat. Water, though, you go out 105 degree day, it takes a while for your temperature to start going up, right? Because water is acting as a natural coolant. The same can be said on a cold day. On a really cold day, what's water going to do before it slows down very much? It's going to slowly release heat, and it's going to keep your temperature pretty constant. Water might be said to be a natural coolant or a natural, what's the opposite of a coolant in your car? What's the other name for it, depending on the season? Antifreeze, right? Coolant and antifreeze are the same thing, just depending on what time you put it in your car. Put it in the summer or put it in the winter. So it's like a built-in, the water is like a built-in system to keep your body temperature constant. And what's the word for that? When we try to keep something pretty constant in our body. Say again? Homeostasis, right? Water allows us to keep homeostasis of temperature. I think we might have mentioned this last time in class too. If you're living out on a desert on an island in the middle of the ocean, what's the temperature probably going to be like there? An island out in the middle of it, completely surrounded by ocean for miles and miles and miles. What's the temperature probably going to be like when that little bitty island out in the middle of the ocean? It's probably going to be pretty much the same all year long. Because when cold air starts coming from, say cold air starts moving out from Canada, as it moves across the ocean, what happens to that cold air? The ocean releases heat and warms it up. By the time it gets to you, it's pretty warm. On the other hand, as hot air starts moving across the ocean, what's the ocean doing to the hot air? It's absorbing heat, cooling it off. By the time it gets to you, it's pretty normal. Places, any kind of land that's surrounded by water, they have pretty stable, normal environments. It's not like our weather here, where it might be 30 one day and 90 the next, right? It's not like North Alabama weather. It's not going to work that way because of water. So that property that I just described is sometimes sometimes recorded as water having a high specific heat. What that means is it takes a lot of heat added to or taken away from water to change what? The temperature. What a high specific heat or high heat capacity really means in terms of biology is you have to add a lot of heat to or take a lot of heat away from water to change the temperature. And all that's because water has what? What makes that happen? What about water? Where do we start this discussion? The hydrogen bonds. To change the temperature, you got to break the bonds. And that takes what? Takes energy. Another thing we'll back up and mention is that water has what's called a capillary action. How many of you have been to the doctor and they took one of those little lancet things and they poked you on the finger? And they took a little glass tube and they stuck it up there and the blood looks like it shot up in the tube? How many of you had that done before? Several. They're going to do some kind of blood test on you. There, right? Now, let's say I went and I took Dylan and I took his finger and I poked it. The blood's not shooting out of his finger, right? So why does it look like it shoots up into the tube when they stick a little glass tube up there? What does that probably mean about the glass tube? But chemically, what does that mean about the tube? It's what? It's polar. And what do we know polar does to other polar things? It attracts, okay? Polar tube attracts polar blood, right? Your blood's mostly water, so it's polar. Pulls it up. It's just like a paper towel. You stick it in water, it'll pull it up because they're both what? Both polar. So that's an example of what word beginning with A that we talked about at the beginning of class today. Adhesive, right? Adhesion. Polar things stick to other polar things. But water can only do that because it is what? Polar. So it all goes back to polarity. Where in biology would that capillary action deal be an important thing? Where in life would capillary action be important? Polar liquids will rise in a polar tube. It's really what capillary action is. Where would that be important? Well, your heart's actually pushing the blood, so it's not so much important in blood. Let's don't think humans. Where else in the real living world might capillary action be important? In living things. Plant roots. Okay? Plant root's just sitting there, right? When it touches water, what does that plant root want the water to do? Go in. What does that mean about the roots? They better be what? They better be polar. So that's the way water initially gets into a plant. Polar water will move into polar tube, polar plant root, and rise up. Is that force strong enough to move the water all the way to the top of, say, a redwood tree? No. It'll only take it a little bit up. So I guess the next question is, how does the water get to the top of like one of those big redwood trees that are several stories tall? Well, I mean, rain obviously rains down on it, but the water that it can use, how does the water get from the ground up to the top, like 5, 6 stories up? There's no heart, right? I mean, the plants don't have a heart. Well, let's think about this. In plants, there are pipes to carry what? And those are called xylem with an X. X-Y-L-E-M, xylem. Those are water pipes. But there's no pump to pump the water. There's tubes, but there's no pump. There's no heart. Eventually, where does that xylem tube starts at the root and eventually ends where? Where in the leaf?
The vein things?
Yeah, but eventually, where does it all end? What's maybe one of the most important things in your leaf that gets overlooked sometimes? Your plant.
The thing on the bottom?
And those are called? Stomata. Stomates. Those are like little holes on the bottom of the leaf, right? Kind of like your what? No. Functionally, what's a stomate in a plant like? What part of your body? Why is it there? Why does a plant have holes in the bottom of its leaves? Slow down. Think about the carbon cycle that we talked about a minute ago. To breathe in,
So it's like a no.
breathe in carbon dioxide and breathe out oxygen. It's like your nose, it's like your nostrils. But as it's breathing in, what else is getting out? If it's breathing in CO2, oxygen's coming out. But what else is coming out? The plant might not necessarily want to come out. Water. If you had a big hole in your skin, water would leak out, right? And that's kind of what's going on with the plant. Water leaks out your nostrils, right? And you don't usually see it in streams, but it's water vapor, it's coming out. You're losing water through any hole in your body. Plants have lots and lots of those holes, right? That can be a problem. But here's the deal. I'm probably not going to be able to draw it up here on the smartboard because the way this thing is working today. But let's say there's a leaf, and you got a little water droplet sticking out this stomate. Sticking out the stomate. Let's try that again. Never mind. I give up. The point being, you got a drop of water sticking out the stomach. What's that water drop connected to? What's right behind that water drop? Another water drop. And what's right behind that water drop? Another water drop. And behind that's another one. And they're all connected up by what? Hydrogen bonds until eventually you get down to where? The root and the water in the ground. Well, this little guy hanging out the stomate, if it's hot or windy, what's eventually going to happen to that water molecule? He's going to evaporate. He's going to take off his water vapor, right? But as he's leaving, what does he do to the guy behind him? He pulls him forward. And what does he do to the one behind him? Pulls him forward. And what does he do to the one behind him? Pulls him forward. Until eventually one gets pulled out of the ground, right? That's the way water moves through a plant. What's the word for that? Anybody know? It's called transpiration. Because it's a lot like what? What process that happens in you is transpiration a lot like? A lot like perspiration, which is what? Sweating. Plant's sort of sweating. When that water evaporates, what does it take away from the plant? When the sweat on your body evaporates, what does it take away from you? Why do you sweat? So you want to get what taken away from you? Heat. Same thing happens to the plant. That's one way a plant helps to maintain body temperature. Transpiration. This transpiration is the process that will move water from root, up stem, all the way to stomach. And it would never happen if water wasn't what? Polar and able to make hydrogen bonds. Let's talk about another one. Water expands as it freezes. When water's in a liquid form, I want you to think of it like chains of water molecules. And one chain can slide past another. That's why liquid water doesn't have a fixed shape. You pour it in any container and it'll take on the shape of that container. But when you start to cool off water, what starts to happen to the chain above and the chain below? They don't only line up, they start to what? They start to form all kinds of bonds between the two chains. Since you got polar waters up here and more polar waters down here, what does polar do to polar? Hydrogen bonds. So now you not only got chains horizontally, you've got the chains connected vertically. And when that happens, you get what? You got ice. But the thing is, when those bonds form between the chains, what does the bond actually do to the chains? When you have the chains that run on top of each other like this, sliding. But when those bonds form, what happens to those two chains? They don't only stop sliding, but they get pushed further apart. Which means they take up more what? More space, they have more volume, which means the ice becomes what? compared to the water it started at. It's the same amount of stuff, takes up more volume. What changed? The density. It became less dense, which means it will what? It'll float. Ice floats. That doesn't sound like that big a deal. But in terms of biology, it's huge. Especially if you're some little fish living in a pond. Let's say you're not living in Alabama. Doesn't get cold enough here for that to be an issue. Let's say you're in Michigan. Okay, Michigan's good. Say you're in Michigan and you're in some small little pond out in a farmer's field in Michigan, and you're a fish, and it gets really, really cold, and the top of the water freezes, and we're in an alternate universe where ice is more dense than liquid water. What happens when the top of the water freezes? If ice is more dense than liquid water, it sinks. And the whole top of the lake just sank. And what happened to you? You just got crushed and drowned, and whatever else happens to you when a big log of ice falls down on you. In nature, that doesn't happen though, because as that top of the water freezes, it floats. And what does that do to the water underneath? What does a coat of ice floating on top do to the water underneath it? It actually acts like insulation, so that it doesn't get wet, too cold. It keeps it warmer. And at first that doesn't sound possible, that if you put ice in water, that the water actually stays warmer. But if you didn't do that, the top would just keep getting colder and colder and sinking, right? And eventually what would you have? If the top just kept freezing and sinking, pretty soon what do you got? A big cube of ice. You're going to be hard-pressed to find solid frozen lakes anywhere in the United States. Because as the top freezes, it insulates everything underneath. It keeps it from getting too cold. Now if it gets cold enough or long enough, eventually you can freeze solid. But that's very, very rare, and the lake would probably have to be what? Very small and very what? Shallow for that to ever happen. It typically doesn't happen. So that's another huge thing for life. As water expands as it freezes, it protects things underneath. It keeps them alive, keeps them from dying out. But the key thing is pretty much all those properties that we just talked about are due to one or two things. Water's polar, forms hydrogen bonds. It's a good solvent, it's got capillary action, it's hard to change the temperature of water, and it expands as it freezes. Make sense? Let's go a little bit further. I think we got another clicker question coming up. We do. So click in your answer to that one. Somebody had 9 or 10, whoever that person is, make sure you're clicking in. You may miss out. Not one poking. He's too late on this one. That's why we're doing these. Alright, C was the correct answer. Let's look at the other choices though. What's dead wrong about choice A? That's what kind of bonds? Covalent, because it's two non-metals joined together, right? B is just wrong. What kind of bonds are inside the molecule in water? Single covalent, right? It's just one bond, H to O on each side. Single covalent bonds. C is the right answer. It's got a unique shape. What's that shape called? Bent, and that allows it to become polar and to make hydrogen bonds between molecules. And we know D is just the opposite of true, right? Because water is what kind of solvent? The universal one. There we kind of see some diagrams of water. This is a Lewis dot diagram with a Venn diagram situation going on. Anybody know what that funny little symbol is there? Looks like an O with a curly Q on top. It's a Greek letter. Anybody know what Greek letter that is? Sigma. It's a lowercase version of sigma. Lowercase sigma. What does it mean there? Because notice it's either sigma plus or sigma minus. What do we say about the water molecule and its charge? We know it's positive on one end and negative on the other. But it's a lot charged or just a little charged? Just a little. Okay? And what that sigma means is it's not even -1 or +1. It's just a little bit charged. So sigma essentially means a little bit. It's what it means in this situation. Just a little charged. Now, notice here's a drawing of lots of water molecules. And what's every water molecule doing to the water molecules near it? What are all those little dots representing? Hydrogen bonds. It's not just hydrogen bonding to one water molecule. It's hydrogen bonding to all the ones around it. And even though each one of those bonds are very weak, collectively they become pretty strong in a hurry because there's so many of them. This one's just showing you that water's really good at dissolving salts. Anything that's ionically bonded dissolves well in water. In salt, the sodium is a cation, the chloride's an anion. What's surrounding that cation? The negative oxygens, right? And what's surrounding the anion? The positive hydrogens. Until eventually, what do they do to this bind between the sodium and the chloride? Pull it apart. And when that happens, what just happened to the salt? They got dissolved. Water is really good at dissolving ionic salts. This diagram is trying to show you the process that moves water through a plant. And again, what did we call that process? Transpiration. Remember that the water first goes into the root through what process actually takes it into the root to begin with? What do we say it's called when a polar liquid rises up in a polar tube? Capillary action. Water goes in. But eventually you get this unbroken chain of water from root all the way up to stomate. And as one drop evaporates, what does it do to the one behind it? Pulls it forward. That's transpiration. Now let's say that Logan over there was trying to find a date, with a lady, and he's having a really hard time. So he bought some roses. He's got this girl who he's got in mind, to go out with, buy some roses, but he has football practice. He bought the roses before football practice. It's really hot. He leaves them in the car, forgets about them. They're in the back seat. What's happening the whole time the roses are in the car? Assuming they're not in water at this point. What's happening to them? What's happening in the stem of those roses? That, transpiration. So the water's moving up the stem and out the way. Stomates. Let's say football practice was really long. O'Connor was mad at him because maybe Logan dropped the pass. You don't do that, right? He'd never do that. But let's say something happened and he happened to drop one. So he has to practice for 3 hours. The whole 3 hours. 5 hours. Okay? The whole time the water's moving up the stem. Logan gets the flowers home. He's going to change clothes hopefully before he tries to go on this day, right? He's been in football practice, and I know that stinks. So he goes and he sticks in the water real quick. Does that do any good? Nope, because where's the water already at? Inside the plant. It's way up the stem already. And this transpiration will only work if what touches what? Water touches water. So what does he have to do to save the plants? What could he do to save them? Take some scissors, go up a little bit and cut them. Cut them above where what happened? Above the level of transpiration. Then stick it in the water and you got water touching water and you're good to go. But it only works if water will touch water. If there's ever a break, and the water in the stem moves up away from the water in the roots, that plant's going to die, right? Because the water can't move through. Water has to be sticking to water for this to work. All right, let's talk a little bit about acids and bases here for just a minute. That's related to water too. Yeah. Another unique property of water is this. Is water an acid or a base? Both. It's both at the same time. And there's a word for that. And there's only a couple of chemicals that this is true of. The word is amphoteric, meaning both. Water's both an acid and a base at the same time. Amphoteric. What does it mean to be an acid? Yeah, they release hydrogen ions, right? This is probably going to be a mess with this board working the way it is. Never mind. Thank you, bro. I'll draw it over here on the board and just describe it for the people who are going to be listening to this. When you put water in a cup, occasionally, one of those water molecules will break apart. What could water break apart into, ion-wise? What ions could water turn into if it split? Well, what do we just get through saying acids give off? What did you say acids give off?
Hydrogen.
Hydrogen ions. Well, what would be left? What other ion would be left if water gave off an H+? OH minus. What's that called? Chemistry people. What's OH minus? Hydroxide. And this is a simple way of defining it. Acids we're going to define as chemicals that give off H+. What are bases? They give off OH minus. Hydroxide. Water gives off both. So it must be both. Right? Both an acid and a base. So acids give off H+. Bases give off OH minus. Water gives off both. So it's both at the same time. Now, that being the case, acids, where are they at on the pH scale? Low, right? From what to what? Where are the acids on the pH scale? 0 up to 7, right? Not including 7, but 0 up to 7. 7 neutral. And then from 7 up through 14, those are bases. 0 up to 7 are the acids. 7 is neutral. Everything above 7 up through 14 is a base. Now here's something that you need to make sure you understand. Really what the pH scale is doing when you measure pH in a solution is it's comparing how many H pluses are in that solution compared to what? OH minuses. If there's the same amount of H pluses as there are OH minuses, what's the pH? 7, neutral. If there's more H pluses than there are OH minuses, what's the pH? It's an acid. If there's more OH minuses than there are H pluses, then it's a base. That's important to know. If H plus and OH minus concentrations are the same, you're talking neutral. If there's more H pluses than there are OH minuses, you're talking acid. If there's more OH minuses than there are H pluses, you're talking base. What does pH stand for, by the way? It's an acronym. You might know what pH actually stands for. It's an acronym you use all the time. Common everyday language. Most people don't know what it stands for. Power of hydrogen. Power of hydrogen. That's what pH is measured. H plus. How much H plus is in there? Now, here's something else we need to make sure that we understand. Out of a cup of water, how many of the water molecules do you think are turning from H2O to H plus and OH minus? Is that something that happens often or not very often? Yeah, it doesn't happen very often at all. So in a cup of water, the concentrations of OH and H plus are really, really small. Like something on the 10 to the minus 7 molarity. What's 10 to the minus 7? What does minus 7 mean? It's when you raise something to the minus 7 power. It's like 10 millionth, right? It's like 10 millionth molarity. Now, it doesn't happen very often. There's very little of it. So it's hard to measure these things. So when we're measuring pH, anybody know what the formula is to calculate the pH of a solution? Yeah, the negative log of the hydrogen concentration. When in science do we use log scales? Because everybody hates logarithms, right? When do we use logarithms? When we're dealing with what kind of numbers? Really, really, really tiny, or what? Really, really, really big. In this case, we're dealing with numbers that are what? Really, really, really tiny. And we'd much rather deal with 7 instead of deal with 10 to the minus 7 power, right? Just makes more sense. But realize the reason we're using logs is because there's not very many H pluses in a solution of water. So instead of dealing with some real tiny, tiny number, scientists and mathematicians have invented this logarithmic scale. But let's say that we had pHs from 0 up to 14. And let's say we had something that was pH 3. What in your body, let's say pH 2. Where in your body might you find a pH of 2? In your stomach. It's the only really acidic place in your body, right? pH of 2. What's the pH of pretty much the whole rest of your body? Keep going up a little bit.
No.
It's kind of a magic number. I want you to memorize this number. The pH of your body fluids is about 7.35. 7.35. It's kind of a magic pH. If your pH was to go up to like 7.55, guess what? You're dead. If it was to drop down to 7.15, guess what? You're dead. Okay? There's a very, very narrow window of pHs that you can exist at. 7.35 is that window, essentially. It's another example of homeostasis, right? We have to keep our pH constant. So let's say we had something that's pH 2. And let's say we had something else that's pH 7. And I ask you, how many times more acidic is the pH 2 solution than the pH 7 solution? What would be your answer? Well, let me ask it this way. How much higher is the H plus concentration at pH 2 than it is at pH 7? Some people would look at it and they would say, well, 1, 2, 3, 4, 5. 5 times higher. The logarithmic scale, though, when you have an log log, what's that number based on? What's a logarithmic scale based on what number? Based on tens. Which means every number actually is a factor of what? 10. So that means a pH of 2 is 10 times as strong as a pH of 3. A pH of 3 is 10 times as strong as a pH of 4. 4 is 10 times stronger than 5. 6 is 10 times stronger than 7. And so on. So we actually have 10 times 10 times 10 times 10 times 10. Which would be what, 1,000, 100,000 times. So what we're saying is a pH of 2 is about 100,000 times stronger than a pH of 7. You just count the 10s between them and multiply it out. Okay? So 10 times 10 times 10 times 10 times 10. Does that make sense? Logarithms are based on the number 10. When you go up 1, you're actually going up what? 10. Let's do a little bit more basic chemistry review here with pH. Acids. How do you look at a formula for something and know it's an acid? Say I gave you a molecular formula and you don't know if it's an acid or not. how could you look at that formula and tell most of the time if it's an acid? Almost always starts with H, right? In chemistry, if it starts with H, there's a good chance it's an acid. What's the acid that you probably use more than any other in chemistry lab? Hydrochloric. Is that found in living things anywhere? Hydrochloric acid. Do you have any hydrochloric acid in you? Other than if you drink some of it in the chemistry lab. Which would be a bad idea, by the way. Turns out that's stomach acid. Hydrochloric acid is stomach acid. You make it all the time. Yes. No, you can. They man make it. They're not giving people on like that. No. They're not. They're not making people for chemistry lab. Hold up, somebody's at the door. Go on in. How can you look at a chemical and know if it's a base? Most of the time, the formula ends in OH, hydroxide. Now, there's a lot of exceptions to that rule. If you've taken AP Chem, you know there's lots of exceptions to that rule. But for purposes of this class, if it's a base, its formula tends to end in OH. What's the most common base in chemistry lab that you probably use? Probably use it in just about every lab you did in Chemistry 1. Sodium hydroxide. Better known to your grandparents as wet, because they used it to make soap. What they used to make soap out of? That old-timey soap. What was it called? What kind of soap? Have you ever heard of lye soap? Lye? Sodium hydroxide. Lye. This next thing I'm going to tell you, this is the last new thing we'll mention. If you don't pay attention to what I'm about to explain, you're going to get lost. Just to be straight up. Listen closely. There are these chemicals that are called buffers. Anybody know what a buffer might be in biology? It's a chemical, or actually it's a system of chemicals that help to keep what from changing. The pH. It's a system of chemicals that help you to keep the pH in your body from changing. A buffer system. Keep pH from changing. And we say that's hugely important because if your pH changes by more than like 0.2 or so, and either way, up or down, what happens? It dies. It's important that you keep it constant. In your body. Actually, before I get to the part in your body, when they make Coca-Cola, what do they do? How do you make Coke? Not that kind of Coke, Coca-Cola. How do you make Coca-Cola? Take water, and what do you bubble into it? Carbon dioxide. Carbon dioxide plus water gives you what? Carbonic acid. But it turns out that the arrows there go both ways. Well, if you have a reaction where the arrows are going both ways, what does that mean? H2O plus CO2 gives you carbonic acid, but what happens to some of that carbonic acid real fast? It turns back into CO2 and water. It's called a reversible reaction. It changes. It can go back and forth. Well, here's the deal. That carbonic acid turns out to be really important in your body. Here's how this works. This equation that I have written on the board, and I'll talk about this for you people watching the video later. This equation on the board is called the carbonic acid bicarbonate ion buffer system. This is carbonic acid, and this is bicarbonate ion. Let's say you're like me, and maybe the worst habit I have health-wise is I drink way too much soda. Way too much. which means I'm constantly putting, other than all that extra sugar and stuff in my body, what else am I constantly putting into my body? Well, that's not even what I was thinking. I'm putting carbon dioxide, but I'm also putting in acids, right? It comes acidic. Which means I'm constantly putting in too much of this. H plus, right? That's whenever you hear acid, think H plus. Well, if that goes up, what happens to the pH of, what should happen to my pH? More H plus means pH should go down, right? Low pHs are really acidic. High pHs, really basic. More H plus, lower pH. But that doesn't happen. And the way that works is this. If all of a sudden my body says, hey, there's too much of this, what does my body want to do? If there's too much of this floating around in my blood, my body wants to get rid of this, right? So what it will do is it will take this reaction going this way, right to left, and it'll speed that reaction up. At the same time, this reaction going left to right, what does it do to that reaction? It slows it down. And notice this reaction going right to left, what is it doing to H plus? It's changing it into something that's not H plus, right? So that's going to lower my H plus in my blood. At the same time, the reaction that's making H plus gets almost stopped. Let's say that Cameron here is at home, and he lets a dirty word slip in front of his mom. And his mom has some of that old-timey lye soap. I'll teach you. Okay? So he washes his mouth out with lye soap. And he swallows some of it because he's fighting, you know. He swallows some of the lye soap. What did we just get through saying lye soap was made out of? No? Sodium hydroxide, which is a base. What do bases do to H plus? They take it away. Okay? So let's say all of a sudden Cameron's body says, whoa, my H pluses, there's not enough of them. So what is his body going to do to get H plus back? What's going to happen with these speeds? It's going to speed up the reaction going to left to right, because what's that doing? Making more H pluses. And it's going to slow this one down, because what's that one doing? Going right to left. That's taking away H plus. So that's one of the main ways your body keeps its pH constant, is by having this buffer system. If you need more H plus, you speed up the reaction going left to right, you slow down the one going right to left. If you need less H plus, you speed up the reaction to the going left, right to left, you slow down the one going left to right. That's a buffer system. It's a system of chemicals that help to resist changes in pH. Mm-hmm.
How many will die of acid overdose or base overdose?
It would be very, very rare. Because you not only have this, what else helps you to keep your pH pretty constant? If you drink too much soda, and you go to the bathroom, urinate. If you really drink too much soda, let's say you went to the movies and you drink like 3 of those big gulp kinds of things, okay, for theater, and then you go pee. What does it feel like? It burns, okay? Because what other organ is helping out with the pH thing? Your kidneys. And your kidneys are taking that extra H plus and dumping them out in the urine, right? Which means what about your urine if it's got a lot of extra H plus in it? It's acidic. And as it comes out, it will burn. Not a good thing, right? Not a good thing. So that's what buffers are. Chemical systems that help to keep pH constant. Let's finish up real quick before we run out of time. There's just an idea of where things fall on the pH scale. Hydrochloric acid, if it's pure, it's about 0. Your stomach acid, which is watered down, right? Still hydrochloric acid, but it's watered down. Somewhere between 1 and 2. Lemon juice is a pH of 2. Would you want to drink a lot of just pure lemon juice all the time? What would it really be hard on? It might be hard on your stomach, but also hard on your teeth. Because as you're dissolving it, as you're drinking, it actually dissolves some of the enamel off your teeth. Soda will do that too if you're drinking enough soda. Slowly it'll eat the enamel off your teeth. Notice Coke, beer, vinegar, they're all in the 3 range. Yeah.
Crops carry 2 liters later in their carbs to wash acid or wash blood off of roads and car wrecks.
Hadn't heard that. Makes sense. I would probably use vinegar, but yeah, it makes sense. Tomatoes are pretty acidic. Coffee's a little acidic. Notice that rainwater is a little acidic. Rainwater is like pH 5.5 or so. How come? Just regular rainwater. As rain is falling through the air, what's dissolving in it? What gas would be important? Look at the board up there. The top equation. As water is falling through the air, some CO2's in the air, right? And if that CO2 dissolves in the rain, what do you got? Top equation. What's the thing on the right? Carbonic what? Acid. It becomes a little acidic as it's falling. Notice that urine is usually a little bit acidic, not too much, but a little. Human blood, about 7.35, like we mentioned earlier. Antacid. An antacid is really what? Base. Antiacid is a base, right? That's what you take it for. So neutralize stomach acid. Sodium hydroxide, notice pure is way down there around 14. All right, we got another clicker question here. Be careful on this one. This should say has increased right there. D just says the solution has become more basic. All right, is that everybody? What's the answer? B. Like we said before, every time you change pH units, you're changing things by a factor of 10. And if you go from 7 down to 6, it's becoming more what? The lower you go, what's happening? The more acidic it's becoming, which means what's happening to the H plus concentration? Going up. More H plus means lower pH. All right, here's another one. Oh, this is something I need to do a little teaching on this. I haven't taught you this. There's another system called pOH, which is essentially the same system, but instead of measuring H plus, it's measuring what? OH minus. Still runs from 0 to 14. If a solution has a pH of 2, what's its pOH? 12. They have to add up to be 14. So if something has a pH of 2, its pOH is 12. If something has a pOH of 8, it's got a pH of 6. They have to add up to be 14. The pH and the pOH have to add up to be 14. That's really all you need to know to answer this question. See what you can do. Change some funny background. All right, so what's the answer?
C.
It is C. And you know that the whole 9 plus 5 thing is easy, but if it's got a pH of 9, anything above 7 pH, you know, is always what? A base. All right, we got another one. Plug it in. All right, everybody in? Don't share. All right, the answer to that one is A, all right? They have to add up to be 14, but the pH is above 7, so it's a base. All right. This is where you need a sheet of paper, because this is your homework. Write that down. This will be due on Thursday. This is another one of those that you can Google and find the rubric, because this came straight off an AP test. I would encourage you to Google it and find the rubric and use that to write a really good free response question. Answer. Don't just wing it. Write a good answer. One thing also while you're writing, Thursday, we're going to run like a normal AP Friday. So your AP classes, you'll only stay for 45 minutes in each one. Friday's schedule is going to be really weird. You guys are going to college day on Friday. Band people, y'all are leaving at like, what, 11 or something? Anybody know what time? 12. You'll have to eat lunch before that. So Friday is going to be pretty much a wasted day. So Thursday, we're going to run like a Friday. I'm going to stop the recording here. Y'all just keep on going.